For question 1d, we are to solve for the complex power phasor S for this circuit, and we're given a load impedance of two parallel components, an inductance and a resistor, and we're supposed to say whether the power factor is leading or lagging. Okay, so how do we solve this? Well, to get the complex power phasor, we have to know what it is, and let's write it out. So that is going to be S is equal to 1/2 the voltage phasor times the complex conjugate of the current phasor. Okay, so now that we know what the complex phasor is supposed to be, we need to find its parts. We know the phasor current, okay, so we know I, and we need V, okay? We need the phasor voltage. So we have to calculate what the voltage is across here. Okay, so how do we do that? Well, we could use Ohm's law, the complex form of Ohm's law, where the voltage is equal to the current times the total impedance. So I've called it ZT. Okay, and where in this case ZT is the parallel combination of the impedance of the inductor in parallel with the impedance of the resistor. So how about on the side we calculate that out. So let's make a little space here and we'll just calculate it out. So what's ZR? ZR, it's given to us as 3 ohms, okay? It's a real quantity and it's 3. What about ZL? ZL is also given to us as J4. Okay, then how do we calculate ZT, the total impedance of these components in parallel? Okay, well, we can, since they're in parallel, we could use kind of our little shortcut for calculating parallel impedance. So it's 3 times J4 divided by 3 plus J4. Okay, so now we have to put this in a standard form. Let's first tidy this up a little bit. So it's J12 on the top and 3 plus J4. So to be able to do anything useful with this, we need to put it in standard form where it's just a real part plus an imaginary part. Okay, we can't have any complex numbers on the denominator. So how we do that is by taking this number, J12 divided by 3 plus J4, and we multiply by the complex conjugate of the denominator. So it's going to be 3 minus J4 divided by 3 minus, J4. Now note that this is the complex conjugate of the denominator divided by the complex conjugate of the denominator, and that's equal to 1. So we're not changing the original number here. Okay? So this is just a little trick that we have to get a number in standard form. Okay? A complex number in standard form. Okay, so let's multiply out. So let's go back to our same color to be consistent. So let's multiply this out. So on top we're going to get 48 plus J36 divided by 9 plus 16. Okay? And that is going to equal 48 plus J36 divided by 25. Okay, so and let's divide it out by 25. So we're going to have 1.92 plus J 1.44. Okay, so now we're going to be having to multiply complex numbers when we go back to the left hand side of the page. So we're going to convert this into polar form. Okay, so what does that look like? There's our real axis, there's our imaginary axis, right? And on the real axis, what we got? 1.92. On the imaginary, we got 1.44. And we want to calculate this guy right here, right? Okay, we want to calculate the magnitude and phase of that point. Okay, so let us do our conversion. So the magnitude, of course, we're just using Pythagoras, 1.92 squared plus 1.44 squared. That's magnitude. And then the phase angle, right, we're measuring from the positive real axis. So it's inverse tan of 1.44 divided by 1.92. Okay, and that is going to work out to a ZT in polar form of 2.4, phase angle of 36.9 degrees. Okay, so now let's go back to the left-hand side and start computing. Okay, so we've got, going back to here, so we've got voltage phasor being equal to the current phasor. So that is 25, that's given right on the diagram, 25 at a phase angle of 90 degrees. And then multiplied by this complex impedance, let's make sure that looks like a degrees. Okay, and multiplying by the complex impedance that we just found over on the right hand side, so that's 2.4 at a phase angle of 36.9 degrees. Okay, and that works out to a magnitude of 60 with phase angle of 126.9 degrees. So remember, when we're doing phasors, we multiply the magnitudes and then we add the phase angles. So this plus this is that, okay? All right, what's our next step? Well, we're going to go back and we're going to solve for the complex power phasor, and so we need to find out what the complex current is, the complex conjugate of the phasor current. So let's just say now we need complex conjugate of the phasor current. So we know that I is equal to 25 at a phase angle of 90 degrees. Okay, and if we convert it to rectangular form, the real part is going to be 0, so we just have an imaginary part, and that's J25, okay? Positive J25. Okay, if we think about the phasor diagram, that's what it works out to. So then the complex conjugate of that current phasor is going to be simply minus J25. And what we do, right, just as a note, we flip the sign on, how about we just say on just the imaginary part. That's how you take the complex conjugate of a phasor. Okay, you just flip the sign on the imaginary part. Okay, so now that we know that, let's calculate the complex phasor. So then S is equal to 1/2 V times conjugate of the phasor current, plug in what we've got. So 1/2, the phasor voltage was, oh no, that wasn't that one. It was 60, magnitude 60, 126.9 degrees. And then the complex conjugate is what we found over there. And we have to we have to convert this one to phasor form. So let's just convert this to phasor form. So it's just going to be magnitude of 25 and a phase angle of minus 90 degrees, right? Okay, so that's what we're going to plug in. So it's going to be 25 at a phase angle of minus 90 degrees. Okay. And then when we go ahead and compute it, next step, so multiply all those together, we have 750, which is multiplying all the magnitudes and the 1/2 as well. And then phase angles are 126.9 degrees plus minus 90 degrees, and that resolves itself to 750 degrees with a phase angle of 36.9 degrees. Okay, so that's the representation for the complex power phasor. So we've got the first part, so it's 750, phase angle 36.9 degrees. Okay, so that's good. And then let us figure out whether we are leading and lagging. So what does that mean? Okay, well, let us draw complex power phasor. Okay, there's a real axis and an imaginary axis. Okay, so we've got a positive 36 degrees. So this is theta. This is the power angle, and this theta is 36.9 degrees. Okay, and we have a magnitude of 750 degrees. Now, is this leading or lagging? Well, when the power factor is leading, so let's think of theta as equal to theta v minus theta I, okay? And it's positive when the voltage is leading the current, and that represents an inductive load. And so theta is positive for an inductive load, and the current is lagging. So let us just make a note. So the current lags the voltage when the power angle is positive. So when it's positive, then the power factor is lagging. Also means that it's inductive, and which is great because, hey, look, there's an inductor there, so it's supposed to be inductive. So now what about if it's if the power angle is negative? Well, then that would be leading, and it would represent a capacitive type of load. Okay, so in this case we answer lagging.